So here we are to talk about USB plug and play made easier with NXP MCUs. So the way we'll do this today is I will start the presentation, give you a quick overview of our overall portfolio, the different families that we have within the NXP LPC MCU portfolio, and then Paul will have the Herculean task of presenting USB in 45 minutes, which I think is never easy. So let's talk about our portfolio. NXP, I think, is a leader in the ARM and MCU space. We have a very clear strategy, and that is 100% focused on ARM. If you look back into time, we were a very strong player in the ADC 51. And then from that point on, we made a switch towards ARM 7, then to ARM 9, and today we have a full range of Cortex-M cores from Cortex-M0 all the way to Cortex-M4. Cortex-M0 basically caters to the 8 and 16-bit applications, the entry-level applications, which need low power, typically low performance, lower cost, all the way to Cortex-M4, which focuses on higher-end communication, digital signal control, and more complex peripherals. So yeah, we have the full range of options, and the best news is that we have USB catering to all these three lines. So we have a USB series in the Cortex-M0 space, we have the USB series in the Cortex-M3, and then M4. A variety of options going from full-speed USB all the way to high-speed OTG, and we'll discuss more about that. These two, I think this is a very interesting point here. When we move between Cortex-M0 to M3, we offer customers a pin-to-pin compatible version. So if you start from Cortex-M0, there will be a migration path to Cortex-M3. Today, if you start with Cortex-M3, you will have a migration path to M4. And it's not just within the Cortex family. When we moved from ARM 7 to Cortex-M3, we offered a migration path from the ARM 7 to the Cortex-M3 land. So that's one of our key strategies as we grow the family, the ARM-based family. Here is a zoomed-in version of the Cortex family that we have today. We are, in fact, today the only vendor that can offer you a fully scalable solution from Cortex-M0 to M4. Again, the way we see the market, we have this continuum vision from M0 to M4. M0 catering to the 8 and 16-bit applications. That's what we're going after with M0. We're talking about low cost here. We're talking about applications which are below the $1 range. Then we go into the Cortex-M3 space, which caters to the high-performance, communication-centric, general-purpose 32-bit applications. And then finally, we go to the Cortex-M4 space, which brings in floating point, which brings in dual core. So we have a very unique solution in this space, where we have a Cortex-M4 and an M0 coexisting on the same package. That's kind of interesting, and I think from the other vendors who are offering M4 versions in the market today. So yeah, dual core. And yeah, USB options scale from Cortex-M0 to M4. So now that you have the view of the M0, M3, and M4, let's talk about the families. So these are the key families that we have within each line. So let me go from bottom to top here. So Cortex-M0, performance-wise, we're talking about execution up to 50 megahertz. We have two main series or families, if you may call it, LPC1100L and LPC1200. So the LPC1100L has flash configurations up to 32K. The LPC1200 extends that configuration all the way up to 128K. Now, within this 1100L series, we have brought in CAN, we have brought in USB, we have brought in segment LCD. In fact, the segment LCD introduction is just recent. We had a press release yesterday talking about the integration of a 160 segment LCD driver into the 1100L series. And this, I think, is our fastest growing family today in terms of the number of products coming to the market. The 1200 is more tailored towards industrial control. It has been certified by Langer, which is an independent entity in Germany that talks about that highlights the immunity of the series. So we have very high immunity, high ESD on the 1200, and it's also been Class B certified. So it's a very good solution for safety critical and white goods applications. So moving on from Cortex-M3, now we go to the from Cortex-M0 we go to the Cortex-M3 space, and here we talk about three main lines: the 1300, the LPC-1700, and the LPC-1800. In terms of USB, we're talking about full-speed device USB with M0. When we go into the M3 space, we bring in high-speed options. Now, the good news is that we have a pin-to-pin version between 1100 and 1300. So today, if you're using Cortex-M0-based USB solution, there's a migration path from the 1100 to the 1300, which is our entry point for Cortex-M3. And then from there, you can find your way into more complex, feature-rich processors, which bring in high-speed USB, CAN, Ethernet, LCD controllers. Yeah, we're talking about a full range of features surrounding the ARM core. And finally, we have the Cortex-M4, which is our recent addition to the entire portfolio, which is today at 150 megahertz. We also are very confident that we can up this performance to 180. And this brings in DSC capabilities into the Cortex-M family. Okay, so before I hand over to Paul, I just want to highlight two main parts. I think that will give you a good range, that will give you a good idea of the range of solutions that we have today with USB. This is the LPC11U100 Cortex-M0 with USB. It's a full-speed USB device. And the strategy for this part was we strongly want to go after 8 and 16-bit applications today, which offer USB solutions. The starting price point is 99 cents at 10K quantities, suggested resale at distribution. But you get the feel, right? I mean, we're offering a 32K flat. We are offering a Cortex-M0 32-bit processor at this price point. So if we do an analysis, we did an analysis of the pricing comparison between the 11U versus some typical competitors in this space, and we saw that you can get up to 40% of cost saving if you use 11U versus the other proprietary 8 and 16-bit processors in the market. So key features, first thing is it's a low-cost USB solution. It offers not just USB, it also offers a smart card interface via the UART, what we call as a USART. It offers two SSPs and an I2C and a UART. I think two SSPs is very critical for some applications, especially if you're in the touch space. You need two SSPs to talk to the touch to the monitors. Runtime, power management. So in addition to the USB drivers in ROM, we also have a new concept called power profiles, which we have brought into the Cortex-M0 family. What the power profiles do is, in runtime, when you are in active mode, you can configure the part towards three areas that we call performance, efficiency, and lowest active mode. So instead of giving the customer more configurations to reduce power consumption, we have encapsulated all of that into a driver, put it on the side in a ROM, and then given the customer and given the application APIs. So while you are running your application, you can just call these APIs and customize the processor towards efficiency, performance, or lowest active power. So yeah, it's a one-stop shop for USB. The USB part, this part is being certified by USB.org. So if you go to USB.org and look for the 11U14, it will show up in the system. So that means that it is compliant with the USB specification. We have drivers. We have free drivers for HID, mass storage, CDC on our website, which you can download and it's free to use. And finally, We offer the 11U in a small 4.5 by 4.5 millimeter footprint package, the TFPGA48. So the innovations that we do are not just in the processor itself, but we also take packaging very seriously. In addition to this, we have a 2.5 by 2.5 millimeter footprint 1100L as well. As I mentioned before, it offers a migration path. If you start with 11U today, there is a migration path from 11U to 1300s. So here's a quick snapshot of the roadmap that you can expect with the Cortex-M0. Today we are here offering 32K of flash, 6K of SRAM, low-cost USB option, supported on our in-house tool platform called LPCXpresso. Going forward, this will go up to 128K. We'll bring in E-square, we'll bring in more SRAM, we'll bring in more package options like 64-pin package, and support for other tool platforms like Mbed. And finally, we will have a 134X, which is our Cortex-M3 option, which will also take you to 64K of flash. Again, pin-to-pin compatibility across the different series. Couple more slides, and I'm taking a full shift towards the higher end series. This is the 1800, LPC 1800 high-speed USB. And you can see with this solution, we are offering, we are going all the way to 1 meg of flash, 200K of SRAM, advanced peripherals like a SPI flash interface. We have 2 high-speed USB controllers on board. It's pin-to-pin compatible with the M4, external memory interface, LCD, 10-bit ADCs, QEI, a range of serial peripheral interfaces, and of course, packaging. So you can see, right, we're going from a low-cost, simple to use, easy to use, full-speed device all the way to a high-performance, fully featured LPC 1800. So from 50 megahertz part to a 150 megahertz part. So we have solutions across this entire range. So here's a roadmap of the higher performance 1800, which shows you that we are bringing in the USB, not just in the 1800, but also in the 1700 series. Okay, so from here, Paul will take over the rest of the presentation.
Okay. Thank you. If anyone's done any USB, everyone knows it's not simple. It's actually very complex and requires specialized equipment, like your bus analyzers and things like that. So it's very difficult to do USB until now. What we've made is has made USB simple by incorporating ROM code drivers in our parts. And we're going to show you how you can do that. Well, let's start with the development tools because, again, inexpensive tools. We talked about LPCXpresso, which is a fully low-cost, fully integrated development tool. So it's software as well as the hardware. So these are the little boards that you'll be given at the end of the class. So and the free version, you get up to 128K. So more than enough to work with these smaller parts. And then the LPC-Link. Actually, if you look at this board, so we have, this is all based on Code Red. So Code Red makes LPCXpresso 128K free. If you need more, you can get 256 for $256. You can go up to 512 for $512. So very inexpensive tool set. Then we also have the boards. So I just showed you the LPCXpresso boards. And then we have base boards to go with that as well. So in addition to just having boards, you actually have like a target board. This is the NGX board. There's also one from Embedded Artist. And these are very inexpensive. The nice thing about these boards is they're actually two pieces. So you get one board, and if you break it in half, you'll actually have the LPC-Link, which is a serial wire debug. So you actually don't need this part on it. The LPC-Link is a high-speed interface. It uses our LPC-3154, which is an ARM9 processor. So it's a standalone JTAG debugger. So again, very inexpensive tools to get you started. I think the LPCXpresso boards by themselves, they cost around $29. So for $29, if you go to DigiKey or Mouser or any other distributors, you get the board plus the processor for less than $30. So when you take a look at the development stage, you can just take the free IDE and the very inexpensive tool. You can actually take the IDE and then you can actually hook it up to a base board like the NGX board or the Embedded Artist board. And then you can actually take this, you can remove that target microcontroller and just hook it right up to your target platform. So a very inexpensive, high quality development tool. We also have good web support for this. So you can actually go, if you want to download it, this is a good place to start. And this will link you to the Code Red's LPCXpresso page. We have forums, resources, and LPC Zone, which are videos. Okay, so we're going to start looking at the LPC 1300 family. The reason I'm going to focus on the 1300 family is that is the part we have now that has the ROM code drivers. So that's what's going to make this really, really simple to do USB. So the 1300 is a Cortex-M3. It is capable of going 72 megahertz. Has low power, very low power, has onboard USB drivers for ISP, mass storage, and HID. And it has a full complement of serial peripherals, like you would expect, the UART, SSP port, fast mode plus I2C, as well as 10-bit analog to digital converter, goes up to 400 kilohertz. Nice thing is pin compatible, so as you go up, you can start with the LPCU type parts, and then you can go up to the 1300 parts, pin for pin compatible. So if you take a look at the 1300, so if you take a look at when you start up the IDE, you're going to have startup files. And start files are just where the exception vectors are. So if you open up the IDE, you're going to see the start files. It may handle system initialization, and it gets you to reset. Now here's the clocking system for the 1300. The important ones for USB are the USB PLL. You actually don't have to use the USB PLL. If you want to run the main clock at 72 megahertz and the USB at 48, because USB requires a 48 megahertz PLL. You can run that at 48 and this at 72, or you can run the whole system at 48 and save some power. Okay, ARM has developed this CMSIS standard, and it defines for Cortex-M microcontroller system common ways to access peripherals. So it doesn't matter whose parts you use, right? If you look at the core, like the NVIC in the part, it'll look exactly the same no matter whose you're looking at. The SysTick timer, all those things are common between everyone's. So CMSIS allows you to actually move between families fairly easily. And again, that was put out by ARM. All our new code is CMSIS compliant. And as you can see, everyone who's in the ARM market has joined this CMSIS standard. CMSIS is kind of confusing. That you're used to headers showing, okay, this UART is at this address, and then all these different registers follow on at different addresses. So here they actually define a structure. And this is 16-bit and 32-bit counter timers. They all look the same. It's just a type def. So it's just a structure. So that doesn't tell us anything other than it shows us what registers. Okay? So then near the bottom of the header file, you're going to see, okay, we have a timer 16B1. There's a 16B0. There's a 32-bit timers. But again, they all use the same structures. So then it tells us it's at this base address. Well, then you're going to have to look at, okay, the base address is the APB base address plus 10,000 hacks. Well, also what it tells you is, okay, the APB base address is 400000. Okay, so what's that tell us? Really, what the address is this plus this, and that gives us the total address. So it's kind of confusing the first time you look at this, but the nice thing about it, you only define like the timer once, right? And that way you can have 4 timers or 6 timers or whatever, or 6 UARTs. They all will look the same, and they'll just be defined in this way. So what would be the PWMC? Well, the answer is actually you start at 4,000, right? And then we know it's the base address and 10,000, and then each of these is 4 bytes. But the one thing you have to remember is these are reserved 3 and 12, so there's actually 15 times 4 bytes in there, because those are each 4 bytes. So that turns out to be 74 if you count all the way down here to the PWMC. So the PWMC is the following address. So CMSIS, the first time you look at it, may be a bit confusing, but once you use it, it's really, really nice. You're going to see this on all our example code, so it's kind of a good idea to understand the basics of CMSIS. In order to, GPIOs are configurable. So each of the IOs, in this case, if we're looking at PIO 2.0, it can be selected as just a GPIO or DTR of the UART. So each pin has multiple functionalities. So you actually have to decide what you want to do. So if you wanted just a GPIO with a pull-up, right, you can leave that as a 0, and we know, okay, pull-up, that's 2, and then I shift it right, 3. So again, this is CMSIS in action here, right? We have an LPCIO con, and then we're pointing within that structure to PIO 2_0. So that's what CMSIS looks like. Important note, don't assume the GPIO is at 0. Sometimes you get burned. It's not always 0. Generally speaking, it is, but I think we've all been who've played with these have been burned assuming that they're 0. There's also a repeater mode that enables the pull-up resistor if pin is in the logic high state. So basically, it's like a bus hold, which is a nice little feature. And there's also hysteresis built into these parts. There's also a direction register. So if you are a GPIO, you can set it as an input or an output. So if you wanted to set GPIO 2 bits 2, 7, and 10 as outputs, you generally use something like this. In 32-bit world, you see this a lot in all our app notes and example code and things like this. Instead of counting 0, 0, 0, 0, 1, 0, 0, 1, we just say, okay, do this, which is just a constant, right? The compiler turns it into constant, so it's not a big deal. If you have any questions, please stop me. This is actually we actually do a full day seminar on this, and I'm kind of getting it done in 45 minutes, so. Okay, so reading and writing to port, that's pretty straightforward. Now we're getting into USB basics. Now the whole thing, we're not going to get in, the whole idea of today's seminar is how easy USB can be. So we're going to show very, very the basics you need to know in order to get USB working. Okay? Which is not very much. I think everyone understands the topology. You have hubs. You have a host, first of all. Out of the host, you can have devices or you can have hubs. And hubs provide the connecting ports, power, terminations, things like that. And then off the hubs, you have devices. Here it shows you that it's a tier-starred topology with the hub. Even the host has a root hub, right? Every host has to have a hub. The root hub can have one or two in our microcontrollers. And then you go down from there. And each segment can be 5 meters. And on function 7, you can obviously only have a function. Right there, you can't have a hub right there. And the maximum cable length then, if you add all the way down, is 30 meters, which is pretty long. There's 4 different transfer types. This is an important thing to know when you're doing USB. There's control, interrupt, bulk, and isochronous. Control is when you enumerate, when you first plug the device in, everything goes over the control port, over the using control transfers. Okay? Maximum speed is 832 bytes, or 1364 transactions per frame. And a frame, okay, today we're only talking about full speed, okay? We're not talking about high speed at all. So, interrupt, you can have 1 64 byte per frame, or 64 bytes per millisecond. So that's not very high speed. Bulk is the fastest transfer method for an otherwise idle bus. Okay. It doesn't mean you're going to get the fastest speed because it's got the lowest priority. Okay. So although you can go really fast, if the bus is busy doing hid and interrupt, or hid is interrupt, your mouse and keyboard and things, you're probably not going to get that full speed. But an otherwise idle bus, bulk is very fast. Mass storage class, for instance, uses bulk. Virtual COM ports use bulk transfers. And then isochronous is things that you have to do in a specific period of time. Audio, for instance, right? You want that audio to come out at a certain period of time. So it's a constant, so it's streaming. If you go to high speed, what they do in high speed is they take that 1 millisecond frame and then they divide it by 8. So you actually have micro frames. And then you actually have, up to, in bulk, 13,500, and they up the size of the data transfers as well. Instead of limited to 64, for instance, in bulk, you can go 13 transactions per microframe. So significantly faster as soon as you go to high speed. One thing, error correction is done in control, interrupt, and bulk. You don't see any in isochronous because if you lose a packet in like audio, you just move on. Okay? Any questions on transfers? No? Endpoints. Endpoints, you have to know about endpoints because what they are buffers, okay? And these, you can have up to 16 endpoints. A device doesn't have to have 16, but it can have a maximum of 16 endpoints per device. Some of our devices have 16, some of them have 5. But it's up, it's up to the microcontroller manufacturer decide how many endpoints they use. Okay, so all USB transfers are targeted to the endpoints, right? So we have from the host to these endpoints. So the endpoints are in the device. And an endpoint is a buffer or a FIFO used to transmit or receive data. Okay? Each endpoint has a direction and address, right? So you can have an in endpoint and an out endpoint. So it has to have a direction as well, except for the control endpoint, which is bidirectional, which makes sense, right? You're in the enumeration process. You're constantly sending and receiving data from the host, trying to, the host is querying at what it is. And again, data flow is in relation to the host. So when you talk about in, it's into the host. Out is out from the host. Okay, so how does a device get recognized by, or how does a host know when a device is inserted into the plug? Okay, so first you're in this state where it's not plugged in yet. Okay, so there's no device plugged in. The host has two 15K pull downs. That's a requirement. The host has that, or the hub has 15K pull downs on its side. Well, on the device side, you have 1.5K pull-ups. On a low-speed device, it connects to the D-. Okay? On a full-speed device, which is all these devices we're talking about today, they're all full speed, you hook it up to the D+ line. Okay, so that's, as soon as that's plugged in, the host knows something was inserted. Okay, then it'll start the enumeration process. High speed starts up actually as a full speed, but then there's some a handshake between the two so that it knows, okay, that's a high-speed device. But again, we don't want to go to too much detail. So there's, in order to get into high speed, there's, during the reset, there's some chirps going on and things like that. Okay, schematics. Here's a typical schematic. In order to create a USB device, it doesn't take a lot of external components. Okay, what are the important things? Oscillator is real important, right? USB spec is 12 megahertz and 25 ppm. Okay, these parts have internal RC oscillators running at 1%. So we can't use those internal RC oscillators because they are 1%. So you use external crystal to achieve 12 megahertz, and then you use the PLL, either the main PLL or the USB PLL, to bring up the 48 megahertz. Okay, so that's very important. And then you have to have an impedance here, which is 45 ohms. And that includes the phi as well as these series resistors. So in our parts, you just have to put 33 ohm resistors there, and you're set. Of course, these are differential lines, so when you lay them out, you want to lay them out as close as possible together to get the noise immunity. ESD protection, it's optional, but it's always a good idea to include that. So we have a full complement of ESD protection diodes, especially for USB. VBus goes to the VBus input, and that tells it if the line is still connected to, it detects whether there's a signal coming from the host. And then we talked about in the previous slide about this 1.5K pull-up resistor, right? So you can actually have that 1.5K pull-up resistor directly connected to a 3.3 to 3.6 volt. But why do we have this? Has anyone seen this before? Okay, let's go into a little bit more detail on this. This one's kind of important, and it snaps a few people who try to go to compliance testing. Okay, so we call it soft connect. So it basically is, here's 1.5K resistor, and then connected to a PNP. You can actually, I would actually change this to a RET, resistor equipped transistor. Instead of 3 components, you can actually use a single transistor. So here you have it through that PNP to the 3.3 volt. In self-powered applications, you probably need to have this feature. Okay, in bus-powered, it probably doesn't matter. Because in bus-powered applications, as soon as you pull the plug out, there's going to be no power here, right? The power goes away. But in bus-powered or self-powered applications, you actually still have a supply. And the USB spec states that the voltage source on the pull-up resistor must be derived from or controlled by the power supplied on the USB cable such that when VBus is removed, the pull-up resistor does not supply current on the data line to which it is attached. Power must be removed within 10 seconds. So if you're designing a thing with that is self-powered, it's a good idea to use this. Because that's called a back voltage test, and they do test that as part of the compliance testing. And what we have in ours is, as soon as VBus is not present anymore, USB Connect is automatically disabled. So what happens is this is turned off. Any questions on that soft connect? Okay. Okay, so on-chip USB driver benefits. Now we're getting to really what we want to get down to today, which is implementing USB device functions. In our parts, we have in-system programming. So the part looks like a mass storage device, and you can just drag and drop your firmware image onto it. Mass storage class and human interface device. And so, we will be including other device classes on future devices, and we'll get to that a little bit later. The nice thing about it is it's really difficult when, let's say I have an example in Kyle or IAR or LPCXpresso, and then I have to convert it to the tools that your company uses, right? And then you have to convert all the code. You don't have to worry about that here, right? Because it's all done in ROM. So it makes your life really easy. Not only that, it's certified. So the first thing we're going to look at is in-system programming. Okay? So this is a really nice feature because it's really fast. And it's a lot easier than generally you use a JTAG or a serial wire debug. And these parts you can use, your SWD, you can use the serial port. But what this part does is it looks at a low level on this PIO 0_1, which is on this board switch 5. And it looks at the state of the VBus. Okay, so this determines whether it goes into ISP. Okay, so if a low on this pin goes, I'm going to go into ISP. And then it looks on this pin, which is VBus. It says if it's high or low, it's going to go either to serial or to USB. So what is a HID device? Data is transferred in structures called reports. So during the enumeration, you tell the host how many bytes you're going to send and receive, how many endpoints you have. You can have a minimum of at least one in point, but you can have one in and one out. Okay? For full speed, again, we're talking about, you can have a maximum of 64 bytes. And again, we're going to use reports, and the reports are structured ways of defining the data. So there's no guaranteed rate of transfer. If the device is configured for a specific time interval, the time between transactions may be equal to or less than this period. And the thing with Windows is it actually doesn't use exactly what you tell it. It usually does it in multiples of 2, 2, 4, 8, 16, 32. I think 32 is the max. So be aware of that. Okay, so if you look at this is what you have to put, this is the part of the code that you have to define, okay? So a vendor ID and a product ID. Why is that important? Well, that's how you match your application to the device. So when your app starts, it's going to go through all these parts and it's going to say, oh, okay, here's the vendor ID product ID match. I'm going to control this device. There's a string descriptors that you can put your own string descriptors in there. In this example, there's 1 byte going in and 1 byte going out. Okay? And again, you can put up to 64 in each direction. Totally up to you. Then you have to tell it the function names of the in report and out report. So you're going to have 2 functions in the code. So, and you tell it what the name of it is. You call it whatever you want, it doesn't matter. But you have to tell it here. And then the interval. So we're going to do every 32 milliseconds. Oops. And then we're going to, in the device info and the device type, we tell it's a human interface device. Again, you're just filling in a structure that we've defined. Okay? And then we go through an initialization process. And again, this is all in ROM, right? And then we give them the ROM this device info. And then what we do need to do is enable a timer, the IO con, and the USB registers. Okay, so that's a requirement. The PLL and init and pin init functions. And then you have a descriptor file. One thing when you're doing the descriptors, like string descriptors, it's done in Unicode. That's not so difficult. All you have to remember is it's the letter followed by a 0. So these are all Unicode strings. So this is just an example, NXP Semicon, okay? And then the USB connect, that's what we talked about before, where we're putting in that 1.5K resistor. If you don't have it in your circuit, it doesn't matter. You don't have to have it, but it allows you to control that 1.5K pull-up resistor. And then within the handler, right, you have a USB IRQ handler. You have to now point to the ROM code, to the ISR handler within the ROM code. So the ROM code now handles the interrupts. Okay? So in this example, we have 1 in and 1 out. So what we're going to do is we're going to control a switch as an in and an LED as an out. So we actually have a demo where we extend this HID with an A, and it reads the A to D. And all I need to do is change the report count to 3, right? Because I want to read the state of the switch plus 2 bytes because it's a 10-bit A to D. I'm not going to demonstrate, I just want to show you quickly. And I have a little GUI there and you can change it. Anyone interested in the code or whatever, please contact us. We can give you all this stuff so you can try it on your own. It's really simple to do. We also have a CDC, which is a virtual COM port. And again, it's just, you know, you can just, using TerraTerm, you can send from one device to the next. This demo is actually at our booth, and it is a mass storage class, but you actually can read and write to an SD card. And that uses our Cortex-M0. Okay? Okay. Okay, so here's some important stuff. What are we working on? High-speed USB. We talked all about full-speed USB today, but we are working on high-speed USB. As Amit had mentioned, the LPC 1800 family, which is a 150 megahertz Cortex-M3, that'll have high-speed host and device. The LPC 4300 family, which is a Cortex-M4. Cortex-M4 is a dual core. It's got a Cortex-M4 and an M0 in it. And that'll support high-speed USB host and device, and will probably go up to 180 megahertz. Right now, planned in ROM is in-system program, which we just showed you, drag and drop, mass storage class, HID, virtual COM port, and DFU, which is device firmware upgrade. Here's something that we have been working on for a few months now. It's called nxpUSBLib. And it's a complete and fully functional USB software library for all USB-equipped LPC processors. Complete source code license is available to NXP customers free of charge. And it will be LPCXpresso or Kyle Microvision or IAR. So we'll have it for all three of those tools. You want to visit this website here, LPCware. We're going to put lots of example code on LPCware. So that's where you'll find all these libraries. So you'll have OHCI and EHCI. If you don't know the difference, OHCI is full speed basically. EHCI is for the high speed host. Now, here's our goal, is to have audio, CDC, HID, mass storage, MIDI, printer, RNDIS, and still image. Right now we have audio and mass storage available in our host. And again, these stacks are going to run on our full-speed devices and our high-speed devices. All four types of endpoints will be supported. And for the device class, we're going to have audio, CDC, HID, mass storage, MIDI, and RNDIS. And we actually have audio and mass storage ready now. You will not find it on LPCware yet. We're still going through some testing phases, but we expect it to be uploaded fairly soon. So I don't know if you want to talk about this stuff.
Yeah. So yeah, that's our last slide basically, which I would highly encourage you to go to the new community website that we have, LPCware. It's an engineer-to-engineer community, and we're going to host a lot more software packages, application notes on this new website. We're also running a new LCD promotion, a contest on LPCware, which is based on our EMWin. You can use the EMWin library from Seger, which is free of cost, or you can use your own library. But the idea is if you create an LCD application on the NXP micros and submit on LPCware, you enter a chance to win a Nintendo 3DS, if I remember.